All right, so we're in section 9.3 now. We're talking about separable equations. And this is the first section in chapter 9 where we actually talk about how to deductively find a solution to a differential equation. If you take a full course in DE, you're going to find that there's all sorts of different ways of solving differential equations, and they all depend on the form that the DE takes. Very, very slight changes in a differential equation can require completely different methods for solving them. So this first approach is kind of the simplest one that we cover in a sense. First of all, the absolute easiest type of differential equation to solve, generally speaking, are the ones that take this form. dy dx equals some function of x. In the previous section, we started by looking at function or DEs of the form dy dx equals f of x, y. So x's and y's can appear on this side. But if only x's, your independent variable, are showing up in this function, then you can solve this differential equation just by integrating. So here's an example. I want to solve dy dx equals the natural log of x over x. Whatever y is, its derivative is this. There are no y's appearing here. This is just a function of x. And this, by definition of what dy dx is, this is the derivative of that. So one way to solve this is to take an antiderivative of this. That means that y is equal to the antiderivative of the natural log of x over x dx, or the indefinite integral. This can be solved with a really straightforward u substitution. Set u equal to the natural log of x, so that du is equal to 1 over x dx. I already have 1 over x showing up in there. So this looks like the integral of u du, which after integrating is 1/2 u squared plus c. And then substituting this back in for u, I get 1/2 natural log of x squared plus c. Okay? And as we've mentioned before, solutions to differential equations tend to come in infinite families. And the reason for that is because at some step in the solution of a differential equation, almost always you're using an integral. It most of the time is not as straightforward as just integrating both sides of the DE that you're given, because typically this will involve more than just an x in it. If we have y's mixed in here, you can't just integrate that. But in this case, we could, and that plus c that we got here is what makes this a family of solutions. Because for every number that I can plug in for c, this will give me a different solution to that differential equation. But like I said, the overwhelming majority of the time, differential equations are not as simple as this one. So we want to look at a case where dy dx is not just equal to a function of x. And the simplest example we can come up with is what's called a separable equation. So we say that a first order differential equation is separable if you can write it in this form. Dy dx equals g of x times h of y. So there's x's and y's appearing here, but specifically it's a function of just x that's being multiplied to a function of just y. So here are some examples of separable equations. Dy dx equals x squared cosine of y. It's a function of x times a function of y. Dx dt equals x over t. It's a function of x times a function of t. And you might be looking at this and thinking, it doesn't look like multiplication, it looks like division. But you can think of this as x times 1 over t. So, this is still a product of two functions if we think of it that way. dp dt equals 5e to the power of p plus t. This one doesn't necessarily look like a product of a function of p with a function of t, but it does when you write it this way. 5e to the p times e to the t, because we have exponent properties that tell us that this is equal to this. Now I have a function of p and a function of t, and they're being multiplied. So that's what makes these things separable. And again, notice sometimes you have to write your function in a slightly different form before you can recognize it as separable. Here are some non-examples. So dy dx equals x plus y. There is no way to write this so that it's represented exclusively as a function of x times a function of y. Here's another one, dA dt equals the natural log of t times a. We do have a product of t with a, but then that product together is appearing in a natural logarithm. So you can't separate that out into a function of t times a function of a. This guy too, dt, so d big T to d little t equals 2 capital T to the power of little t. This thing is not a product of a function of one t with the other. It's an exponential function. So this is going to be represented in a different way. These are not separable. But we want to work specifically with separable differential equations, and we're going to develop a solution method that works for all of them. So let's suppose that we have a dE that takes that form that we mentioned up here. dy dx equals g of x times h of y. We want to put this in a slightly different form, so I'm going to define I'm going to define a new function p of y to be the reciprocal of 1 over h of y. What that means is I could alternatively write this as g of x over p of y, which if I multiply both sides by p of y would give me this. P of y dy dx equals g of x. Okay. Now, if you notice, I have a y inside this function, and then I have a dy dx showing up on the outside. So changing my notation, another way of writing this when we recognize y as a function of x is p of x, y prime of x equals g of x. Again, remember, y is not an independent variable. It is always a function of x in these problems. To me, this left-hand side looks a whole lot like the chain rule. So that would mean that this is the derivative of a composite function. And if it's already the derivative of something, I can integrate it and kind of undo that derivative with an antiderivative. So I'm going to integrate both sides of this equation now. Okay, so the integral of p of y of x times y prime of x dx is equal to the integral of g of x dx. If I substitute y for y of x, then dy will equal y prime of x dx, so that this thing simplifies down to p of y dy, and on this side I have g of x dx. Now I'm going to leave this here because if you notice what's happened is I have an integral on my left and an integral on my right. This one is a function of y, and I'm integrating it with respect to y. This one is a function of x, and I'm integrating it with respect to x. So what I would do now is evaluate both of these integrals and attempt to solve the result of that for y, which we're going to show how that works in examples. But this technique is called separation of variables because it's taken our equation and moved everything with a y in it to one side, including that dy, everything with an x in it over here, including that dx. And the key to making this work in actual examples is to think of that dy dx as if it were a fraction, and then multiplying both sides by dx to get that dx over here, and then dividing both sides by g of x to get, by h of y to get that h of y over here, and that's called separating variables. Let's do an example to see what that looks like. Okay. So in this first one, I want to solve dy dx plus 2xy squared equals 0. This is a separable equation. But it's not immediately obvious why. So let's first put it in this form. dy dx equals negative 2xy squared. Okay, so that's the form we want it to be in at first. Notice that this is a product of a function of x, negative 2x, with a function of y, y squared. That's what makes it separable. My next goal is going to be to separate variables. So I want to multiply both sides by dx to get this dx over here, and divide both sides by y squared to get that y squared over there. So now I have dy over y squared equals negative 2x dx. Okay, and it may be a little bit weird doing this because in Calculus 1 we try to teach you that this dy dx is not actually a fraction, it's just notation for a derivative, but now we're treating it like a fraction, and the only reason we're able to do that is because of this justification we gave here. Okay, this is justified by all of this work, so we can safely think of dy dx like a fraction now. From this step, I would want to integrate both sides. So I'm going to integrate both sides of that equation. on the left-hand side, I'm integrating with respect to y. That would be negative 1 over y squared. On the right-hand side, I'm going to get negative x squared plus c. Now, I'm going to mention something here that's really common in the study of differential equations. We sort of take advantage of the fact that this is an arbitrary constant, and in a certain way, it's going to absorb a lot of other arbitrary constants that are going to show up, or just constants in general. So here's what I mean by that. First of all, I just took an integral of both sides. Technically, shouldn't I have gotten a plus c over here as well? Or to be a little bit more specific, maybe a plus c1 here and a c2 here, because I have no reason to assume that they're the same constant. Technically, yes, but if I did that and I wrote a constant here, I could just subtract it from both sides, and now over here I have some arbitrary constant minus some other arbitrary constant, which is just an arbitrary constant in its own right. So to keep things concise, we really only need to write plus c on one side, and I'm going to put it here. Okay, here's the next thing I want to do. I want to try to get, that should be a y to the first power, sorry. I want to get that y by itself, so I can multiply both sides by a negative 1 and get 1 over y equals x squared plus c. Okay, now again, you might be looking at this and thinking, shouldn't that be minus c? Because I have a minus here and I multiply both sides by a negative, that plus should change to a minus. But again, that plus c is an arbitrary constant. If we multiply it by a negative 1, the result is still just some arbitrary constant. And I have no problem giving it the same name, because in a sense that c is just absorbing the constants that we throw at it. Now I want to take a reciprocal of both sides so that y is by itself, and I get y equals 1 over x squared plus c. This thing right here is the solution to this differential equation. And again, it's a family of solutions because that c can be whatever I want to plug into it. It's worth, in your own notes, like verifying that this is in fact a solution to this. And we've talked about how to verify if a given function is a solution to a DE. So maybe try that on your own, see if this worked. Okay, let's try another example. This time it's going to be an IVP. We have an initial condition attached to this differential equation. But here we have dy dx equals y squared minus 1 over x squared minus 1. This is a separable equation because it's a function of x, 1 over x squared minus 1, times a function of y squared minus 1. So we can separate variables. I would get dy over y squared minus 1 equals dx over x squared minus 1. Okay, so I'm going to integrate both sides of this thing. But in the process of doing that, notice that the integral on the left and the integral on the right are technically the same integral, just with a different label, a y here and an x here. So if I can find the indefinite integral of one of these, then I'll automatically know what the other one is. I just change those y's into x's. So let's try that. This guy right here is the type of integral I would use partial fractions on. So we have 1 over y squared minus 1, which I know can be factored to 1 over y minus 1 y plus 1, which I can also write using partial fractions as a over y minus 1 plus b over y plus 1. Okay, using the method of partial fractions, we clear the denominator and I get 1 equals a times y plus 1 plus b times y minus 1. And then if you remember how we did this back in chapter 7, I plug in values for y that make one of these two terms go away. So for example, if I plug in a 1, then 1 minus 1 is 0, that goes to 0. I'm left with 1 equals a times 1 plus 1, or 2a. This implies that a equals 1/2. Do the same thing for y equals negative 1, because that's going to make this term go to 0. I'm going to get 1 equals b times negative 1 minus 1, or 1 equals negative 2b, which is the same thing as b equals negative 1/2. Okay, so what this tells me is that this is 1/2 over y minus 1 minus 1/2 over y plus 1. So this is easier to integrate. First of all, the 1/2 that's appearing in both of these numerators can just be factored all the way out of the integral like that. And I'm left with 1 over y minus 1 minus 1 over y plus 1 dy. Both of those give me natural logarithms. This is equal to 1/2 times the natural log of y minus 1. Actually need absolute values there, so let's put an absolute value there, minus the natural log of the absolute value of y plus 1. I'm going to combine these using a logarithm property. I can write this as 1/2 times the natural log of y minus 1 over y plus 1. Okay? So that's what happens here. If I did the same steps on this right-hand integral, I'll get the same thing, except I'm going to have x's where I have y's. So this is going to tell me that 1/2 times the natural log of the absolute value of y minus 1 over y plus 1 is equal to 1/2 times the natural log of y minus 1, or sorry, x minus 1 over x plus 1 plus c. Okay, I can do a little work to simplify things down, but I'm not going to worry about that quite yet. Instead, what I want to do is notice what's going on with this. Actually, you know what? I am going to do a little bit of work. Let's multiply both sides by 2 to clear the 1/2 there. Okay, if I did that, then technically we would see a 1/2 c appearing here, but like we said before, it's an arbitrary constant, so multiplying it by a 1/2 still results in an arbitrary constant. Then I have natural logs appearing on both sides. If I did e to the power of both sides, I'm going to get the absolute value of y minus 1 over y plus 1 equals e to the power of the natural log of the absolute value of x minus 1 over x plus 1 plus c. But this can be written this way. Because I'm using an exponent property. And again, c is an arbitrary constant. E to the power of c is just another arbitrary constant. So I can write this as c times, and then these are going to cancel, absolute value of x minus 1 over x plus 1. Okay, so I can continue working through some simplification stuff here to try and get a value for c, or to try to get y by itself. But rather than do that, what I want to do is see if I could figure out what c is. So up here, I have this initial condition, y of 2 is equal to 2. Okay, I can plug a 2 in for y and a 2 in for x on both sides of this and attempt to solve for c. So if I use my initial condition, IC stands for initial condition down there, then plugging a 2 in for y is going to give me 2 minus 1, 1, over 2 plus 1, 3. I have the absolute value of 1/3, which is just 1/3. Over here, I'm plugging a 2 in for the x's as well. I'm going to get the same thing. So this equals 1/3 c, which means c is equal to 1. Okay? Finally, plugging a 1 in for c here tells me that y minus 1 over y plus 1 is equal to the absolute value of x minus 1 over x plus 1. And I don't think I mentioned that there's an absolute value here, but I wrote it. So for what values, for what function of x that I can set y equal to will this be true? Well, notice these, both the right and left-hand side of this thing look identical to each other. The only difference is that I'm using y's in place of x's over here. So pretty clearly, one solution to this would be y equals x, right? Because if I substituted a y for all of the x's, then I just get a mirror image of what I'm seeing here. So we could do like a whole algebraic approach, but you can kind of just make that observation as well and say that y equals x is totally a valid solution to that. Okay, we have a little bit left to do, but I'm going to do that in the next video.